Hey everybody, this is Mr. Bortnick for AP Calculus AB. We're in Unit 1, Limits and Continuity, and today we're discussing topic 1.7, Selecting Procedures for Determining Limits. Enjoy! All right, for today's notes, 1.7, Selecting Procedures for Limits, we're going to really highlight two special ways that we can use algebra in order to simplify limits. And so these are two special techniques that we're going to be approaching. But in order to do that, I wanted to first give us some quick review from last year and from Algebra 1 about rationalizing functions. So specifically, let's talk about this equation. So for example, 1 over the square root of 2. Not an equation, but an expression. So we have the expression 1 over the square root of 2. Now in general, what I'll mention is that in higher level math, we do not leave answers like this. We do not leave answers, like final answers, with radicals in the denominator. So we do not leave answers with radicals in the denominator. And so because of that, sometimes when we have these fractions and we have square roots in the denominator, we need to do a technique which is called rationalizing the denominator. So we are rationalizing the denominator. And so in this case, all we would do if I wanted to rationalize the denominator is I'm going to multiply this, this fraction, both the numerator and the denominator, by the square root that's in the denominator. Now notice here what that does is now I have 1 times the square root of 2 in the numerator, and in the denominator I have square root of 2 times the square root of 2, which is the square root of 4, which is just 2. So we can simplify this and say that this is 1 square root of 2 over 2, or just the square root of 2 over 2 as our answer for this. And notice, by doing this technique, now I don't have a square root in the denominator anymore. We would say that our answer has now been rationalized. I'm going to show some more examples of this rationalizing technique. Let's try one a little bit more complicated, but not much more complicated. How about 5 over 2 root 3? Again, I cannot leave this as a simplified answer in any higher level math class. And so what I'm going to do here is I'm going to multiply both my numerator and denominator by just the radical part in that denominator. I'm going to multiply by just the square root of 3 in both of those. And so now my numerator is going to become 5 square root of 3. In the denominator, I've got 2. And then if we were to multiply that root 3 times that root 3, that becomes the square root of 9, which itself is just 3. So if we're going to simplify this fully, I have 5 square root of 3 in the numerator, and I've got 2 times 3 in the denominator, which is 6. This cannot be simplified any further, so that is going to be our final answer for that problem. This type of problem also comes up in expressions like this, where we're adding. So I have 2 over 3 plus the square root of 7. Ooh, 3 plus the square root of 7, as opposed to multiplying like we were in the last example. In cases like this, as an aside, we're going to use essentially for a method to get rid of this, we're essentially going to use difference of two squares in order to do this. So difference of two squares. This keeps coming up a lot, that review from 1.6a. And that difference of two squares, if you remember, is the one that says that a squared minus b squared is equal to a plus b times a minus b. What we're going to do here is I'm trying to think of like how I can get rid of the square root. And what I'm going to do is I'm going to multiply by the conjugate. So the conjugate of the radical. So I'm going to multiply with this thing called the conjugate of the radical. And in this case, I'm going to show this work here on the side, and then we'll come back to it. But what I'm going to do here is I'm going to multiply both my numerator and denominator by 3 minus the square root of 7. And 3 minus the square root of 7. whatever I'm going to multiply by is going to have the opposite sign of what's there. So because that was a plus, I am multiplying by a minus. If it were a minus, I would multiply by a plus. For this side work over here for the denominator, we're going to have 3 plus the square root of 7 times 3 minus the square root of 7. Because I have an expression being multiplied by an expression, I would need to expand to find out what this value is. And we could do, again, from our previous lesson, we could do either FOIL or we could do an expansion box. But if we do that, we're going to see 3 times 3 is 9. And then we've got 3 times negative root 7, so that's minus 3 root 7. So 3 times 3, 3 times negative root 7. Now if I do the insides, plus 3 square root of 7, and then our last ones, root 7 times root 7, or root 7 times negative root 7 is going to give me a minus 7 here for that. And what we notice if we do this is that these terms in the middle end up being opposite of one another. They're going to be opposite of one another. And so because of that, they're going to cancel each other out. And this is by design because we picked this thing that was called the conjugate of the radical. Those middle terms are going to go away. Also, notice that when we multiplied the root 7 times the root 7, that the square root went away there as well. So we're left with just 9 minus 7, which is just going to be equal to 2 for that. And there's no square root at all if we do that. And so if we go back to our original problem, this then is going to be in the numerator 2 times 3 minus the square root of 7. In the denominator, we just saw if we multiplied this expression by that other expression, that's going to end up being 2. And then we can also see that now the 2's in the numerator and denominator would cancel each other out. So this is going to be equal to 3 minus the square root of 7. This is a fine answer, specifically because there is no denominator and there's no square root in the denominator. But these would be equivalent to each other. So these would be the same thing if we're going to do that. All right, last one I want to do just as an example of multiplying the conjugate. Yeah, actually we'll just leave it there for that. I think that's going to be a good spot to do that before we get into today's problems. So 1.7 procedures of like limit problems and selecting procedures of limit problems. We've got this problem. We notice immediately, hey, the instructions are here, say rationalize fractions with radicals. So we're going to be using this rationalization technique to algebraically manipulate these and find the limits for these values. And so what I'm going to do here, first off, thinking back to last lesson, we know that our first step in these types of problems where they give us the equation is to do direct substitution. And so if I were to do that, that would be the square root of 5 plus 4 minus 3, all divided by 5 minus 5. That square root of 5 plus 4 would be the square root of 9, so that's just 3. And so then I have 3 minus 3, which is 0. 5 minus 5 is 0. Hey, this is indeterminate form. Because I've got that indeterminate form and because I got that 0 over 0, sort of gives me an idea that, hey, maybe if I try one of these algebraic techniques of simplifying, that I might be able to find the limit. So that gives me a little bit of confidence to try this out. What I'm going to do is I'm going to take that limit as x approaches 5 of the square root of x plus 4 minus 3, all divided by x minus 5. And I'm going to multiply by the conjugate of the numerator. Now, it's not really a problem if there's a square root in that numerator, but I know that if I were to simplify this, that I might be able to find the limit. And so multiplying by the conjugate is a way to move that radical, and it might work out where we're able to actually find this limit. So in this case, I'm going to multiply by the conjugate of that numerator. I'm going to multiply by the square root of x plus 4, and because this was a minus 3, I'm going to have a plus 3 for that conjugate. And I need to multiply this expression in both the numerator and the denominator. So that's the square root of x plus 4 plus 3 divided by the square root of x plus 4 plus 3. In that numerator, if we're to multiply this out, so I have this times that, I'm going to do just a quick expansion box to visually show you what we've got. So it's the square root of x plus 4 minus 3. I've got the square root of x plus 4 plus 3. Here's my little quick expansion box, thinking back to last lesson. The square root of x plus 4 times the square root of x plus 4. Hey, those square roots are going to cancel each other out and give me just an x plus 4. And then I would have 3 times the square root of x plus 4, so 3 square root of x plus 4. And then a negative 3 square root of x plus 4 if I multiply those. And then 3 times negative 3 is negative 9. Notice, by design, because I picked conjugates and multiple of the conjugates, that these are going to cancel each other out. They're opposite signs. One's a positive 3 and one's a negative 3. So that means that that whole numerator is going to become simply x plus 4, coming from right there, minus 9, coming from right there, which if we simplify is simply x minus 5. Nice. Well, let's get back to our problem. Now that we've simplified that numerator, we've got the limit as x approaches 5. That numerator simplified and became x minus 5. Right? That's what we just got from right here. And then the denominator, you might be thinking, hey, I should expand this and do an expansion box in the denominator, but I'm going to leave it the way it is. I'm going to leave it in its factored form, x minus 5 times the square root of x plus 4 plus 3. And conveniently for us, we notice maybe, hey, I got an x minus 5 in the numerator and an x minus 5 in the denominator. Those are going to cancel each other out. Nice! That's going to make this a little bit simpler. So we've got the limit as x approaches 5 of, well, what's left over is in the denominator, and we have to have something in the numerator, so there's going to just still be a 1 up here. And that's 1 divided by the square root of x plus 4 plus 3. Now that I have this simplified, I'm going to go back and try direct substitution again. And I'm going to plug that 5 in for this equation. If we do that, we're going to say that this is equal to 1 over the square root of 5 plus 4 plus 3, which is going to equal 1 over the square root of 9, which is 3, plus the 3, or 1 over 6 as our answer for that problem. Nice technique. Multiplying by that conjugate allowed us to be able to solve that specific one. All right, let's try this with a different one. Problem number 2 says the limit as x approaches 10 of x minus 10, all divided by 3 minus the square root of x minus 1. Same story as before. We always try direct substitution first. And so if I do my direct substitution, this side work, notice I'm not saying that it's equal. We would have 10 minus 10 divided by 3 minus the square root of 10 minus 1. So that would become 0 over 0, or indeterminate form. Again, giving me some confidence here. Ooh, I got indeterminate form. Maybe if I do an algebraic technique, I can find the limit. So what do I multiply by here? Well, we've got that radical in that denominator, so I'm going to multiply by the conjugate of that radical. In this case, that's going to be 3 plus the square root of x minus 1, and 3 plus the square root of x minus 1. I'm going to multiply that in both the numerator and the denominator. We know that by multiplying in the numerator and denominator that it's going to make the fraction stay the same, right? By multiplying that same value in both places. So if we expand, and I could do my work over here on the side again. So 3 plus the square root of x minus 1, that should be a minus 1. And if I do a 3 minus the square root of x minus 1, and we do our little expansion box here, I got 3 times 3, which is 9. Then I've got 3 times negative square root of x minus 1, so that's negative 3 square root of x minus 1. 3 times positive square root of x minus 1 is positive 3 square root of x minus 1. And then the negative times the positive is going to give me a negative x minus 1. Those square roots canceling each other out. Same deal as before. Hey, we've got opposites here. This is going to cancel with this, which is nice, which means that this is going to be equal to 9 minus the x minus 1. Or, if we distribute that negative, this is going to be 10 minus x for that. All right, so let's continue on in this problem. Now that we've found this, we're going to use this over here. So this is going to be equal to the limit as x approaches 10 of that numerator, which we have not yet multiplied, so I'm going to leave it factored. So x minus 10 times 3 plus the square root of x minus 1. And that denominator we just showed is going to equal 10 minus x. Oh, these are so close to canceling each other out. I notice here that I got an x minus 10 and a 10 minus x. If they were the same, I could cancel them out. So the question is, how could I make them the same? And what I'm going to do is I'm going to actually just factor a negative sign out. And so what we're going to have if we do that is this is the limit as x approaches 10 of all the same stuff, x minus 10 times 3 plus the square root of x minus 1. But in the denominator, I'm going to factor out a negative 1. So this is a negative 1 times, now if I do that, what's left over? X minus 10. Again, we could always check to make sure that that makes sense, because if we were to distribute that negative to both of these things, we'd be left with this up here. So we'd have this. Why did I do that? Well, now I've got the exact same thing in the numerator and denominator. These are going to cancel each other out, which is super nice. And so to wrap this problem up, this is the limit as x approaches 10 of 3 plus the square root of x minus 1, all divided by what's left in the denominator is just negative 1. And if we do our direct substitution, if we plug that 10 in, we're going to get 3 plus the square root of 10 minus 1, all divided by negative 1, which looks like that's going to give me negative 6 as my answer for problem number 2. All right, let's continue on to number 3 and number 4. So while those previous problems that we had focused on square roots, we're going to talk next about algebraic techniques to deal with complex fractions. So how do we do these limits in these special problems where we've got these fractions with fractions in them? Aka complex fractions. Now, similarly to our previous problems, we know that really our first step in any problems that we have that they give us the equation is to try direct substitution. So direct substitution, if we do that, we would have a 0 for this in the numerator for that x being divided by 1 over 0 minus 4 plus 1 over 4. So that would be 0 over negative 1/4 plus 1/4, which would be 0 over 0. We've got indeterminate form, which gives us an idea that, hey, maybe if we try some algebraic techniques, we can simplify this. And so let's do that. For problem number 3, the limit as x approaches 0 for this equation, x over 1 over x minus 4 plus the 1 over 4. Here's the problem. If I'm going to try to multiply by something, the thing that's really making this difficult in this problem is that these two denominators are not the same. It would be really nice that if I could combine these two fractions into one, and the only way that I could do that is if they were the same denominator. So what I'm going to do is I'm going to make them the same denominator by multiplying values in the numerator and denominator for each of these. Specifically, I'm going to multiply my first fraction by 4 over 4. So 4 over 4. And I'm going to multiply my second fraction by x minus 4 over x minus 4. You'll notice that all I really did here was just multiply by the other denominator. And so if I do this, what happens? Well, we still have our limit. We haven't taken it yet, so I'm going to still write it. Limit as x approaches 0 of x over a whole bunch of stuff. So over here we've got 4 times 1, so in that numerator is a 4. And then in the denominator I've got 4 over x minus 4, because those got multiplied. Then over on the right side of this fraction, I've got an x minus 4, and that's being divided by that 4 times the x minus 4. Notice, now, because I multiplied this, that these denominators are the same, which means I can combine these into one fraction, which will make this a lot easier to see what's going on. So I'm going to rewrite. This is the limit as x approaches 0. That x, it's still up there in the numerator. But now, because we're adding these two fractions together, this is now going to be 4 plus that x minus 4 all over one fraction, so 4 times x minus 4. And what we also might notice is that our 4 and our minus 4 are going to cancel each other out. So even further, we can simplify, and we can say that this is going to be equal to the limit as x approaches 0 of x divided by, well, those 4's canceled, an x over 4x minus 4. So those are going to be simplified. Looks like it's getting a little bit more simplified. I'm going to also notice here that we have a fraction being divided by another fraction. So one way that I can do this is I'll show a quick example. So it's a little bit of side work over here. If I have like the fraction 1/2, and that's being divided by, let's say 3 over 6. Oh, that's a bad example because those are the same fraction. Let's say 3 over 5. One way that I could rewrite this, a fraction divided by a fraction, is having that 1/2 times the reciprocal of the denominator. So the reciprocal of that fraction, which would be 5 over 3. And so that is a different way that I could write this. So since I'm dividing by this fraction, one way I could simplify this is to multiply by its reciprocal of that denominator. And so this is the limit as x approaches 0 of x times the reciprocal of the denominator, 4 times x minus 4, all over x. Now we can see that these x's actually cancel each other out, which is nice. And we're left with just this expression, 4 times x minus 4. And this is, so much simpler than what we started with. Took a little bit of work in terms of working with the fractions, but now all I need to do to wrap this problem up is to do direct substitution, plug that 0 in, and if we do that, we're going to end up with 4 times negative 4, which is negative 16, for our final answer for problem number 3. We're going to move on to our last problem for today in terms of examples, and that's going to be the number 4, the limit as x approaches 0 of 1 over x plus 3 quantity squared minus 1 over 9, all divided by x. Same as before. For time purposes, I just want to emphasize, if I were doing this from scratch, I would definitely make sure that I was plugging in 0 first to do direct substitution. If you do that, though, we're going to be dividing by 0. We'll have a 0 in the numerator. This is an indeterminate form problem. Trust me, but let's get to doing this. So same technique as before. What I'm trying to do in the numerator is make these have the exact same denominator so that I can combine these fractions into one. I'm going to multiply by the other denominator. So I'm going to multiply here by 9 over 9. And over here, I'm going to multiply by x plus 3 quantity squared over x plus 3 quantity squared. If we do that, we're going to say that this limit as x approaches 0 of, 9 over 9 times x plus 3 quantity squared minus x plus 3 quantity squared over 9 times x plus 3 quantity squared. And then don't forget that that was all being divided by x. Now, since these have the same denominator, this is the limit as x approaches 0 of 9 minus the quantity of x plus 3 quantity squared, all divided by 9 times x plus 3 quantity squared, all divided by x. All right, so now that we're at this point, I'm looking for things that are going to cancel, and I don't quite see them yet. So what I'm going to do is I am going to expand this this fraction in the this numerator of this x plus 3 quantity squared, and to allow some things to cancel. So I have the limit as x approaches 0 of 9 minus, well, if we expand, that's going to be an x squared plus 6x plus 9, and that's still being divided by the 9 times quantity x plus 3 squared, all being divided by x. Why did I do that? Well, we notice now that our 9 and technically our negative 9, because there's this negative in the front, are going to cancel each other out. And we need to remember, of course, we're going to need to distribute that negative sign to each of the things inside of this. And so if we do that, this is going to become the limit as x approaches 0 of, well, those 9's canceled out. So negative x squared minus, don't put a plus, negative x squared minus 6x, all divided by that 9 times x plus 3 quantity squared, all divided by x. Now, instead of writing all divided by x, I'm going to use our technique that we sort of used earlier in order to split that fraction up, like we did here sort of in the green on the left side. And what I'm going to do is I'm going to say, actually, instead of dividing by that this is the same thing as multiplying by 1 over x. That'd be the same thing as dividing by x, is the same thing as multiplying by 1 over x. Well, that's going to allow me now to cancel out some x's from the numerator with that x in the denominator. And so if we do that, this is going to be equal to the limit as x approaches 0 of what looks like negative x minus 6 divided by 9 times x plus 3 quantity squared. Now that we've canceled, we should now be able to wrap this problem up by doing our direct substitution and plugging that 0 in for both of these x's. If we do that, this looks like the numerator is going to go to negative 6, and the denominator is going to go to 81. And so if we simplify that fraction, which we should always do, that's going to give us a negative 2 over 27 for our final answer for this limit. We just went over two special techniques for algebraically finding the limit. One was rationalizing the denominator using the conjugate, and the other was working with these complex fractions. Try the practice problems that we've got that start here, and then check your answers. Good luck, and have a great rest of your day.